Excellent. Okay. Okay. So I'm going to talk a little bit about Faraday's law, and I'm going to talk a little about the exam rubric, and then we are going to practice with the exam for extra credit. So let me first talk a little bit about Faraday's law. Okay, so I'm going to talk a little bit about Faraday's law by first talking a little bit about the magnetic field. So the magnetic field, I'm going to draw a picture here of like a wire that has some current running through it. And I want everyone to think a little bit for a moment about what the magnetic field looks like in this scenario. And if you are drawing a blank, which would be completely understandable, if you're drawing a blank, I would recommend Googling magnetic field due to a wire, and you'll find a bunch of really nice pictures. Okay, so let's just have everyone ponder this for a few minutes. What does the magnetic field look like? Okay, does anyone want a few more minutes to look this up? All right, so let me go ahead and Google this. Oh, actually, I have a demonstration ready to go related to this, so I'll just use that. Magnetic field around a wire. Okay, so this right here is a picture. So let's talk about this picture very briefly. This picture is actually showing the electric field and the electrons flowing opposite the electric field. So what's happening here is F equals QE. The electrons are negatively charged, and so the force that they're feeling is opposite the direction of the electric field. So this is a current flowing through the wire, and what you can see is this magnetic field curling around the wire. Let me put this link in the chat in case you'd like to play around with this. This is one of the first simulations that I've shown that's not a FET simulation. FET doesn't have a lot of magnetic field simulations, to my infinite sadness. They have some other simulations that we're going to use, but they don't have this exact simulation. Okay, so here what we're seeing is that when we have a wire that has current running through it, the magnetic field curls around that wire. So let me write that down in our OneNote. And I'm talking about this because the Faraday's law is very analogous to this. So what I'm going to do is I'm going to draw this here, and the magnetic field kind of goes around tangentially. So there's a couple ways. That we can. So this is the picture. What I want to point out is that there's a right-hand rule that's frequently talked about here. And for that rule, what you do is you take your right hand You place your thumb so that your thumb is pointing in the direction of the current, and then your fingers show you what the magnetic field looks like. So if you kind of like take your thumb and point it here, then your fingers end up showing you what the magnetic field looks like. You can kind of see how they wrap around in a similar way. Does anyone have any questions? This is supposed to be a hand. Okay, any questions so far? Okay, the equation that we used for this was the Biot-Savart law. So the equation that we used was dB vector equals mu naught over 4 pi I dL vector cross. Sorry, not R vector, R hat. Divided by R squared. I'm gonna, just for those of you who are really helped by equations, I'm gonna say the Maxwellian version of this. So Maxwell's laws are used to describe all electromagnetic. A that we is del cross B is equal to J. And what this is this is a mathematical way of saying exactly what the picture above shows us. So this del cross is the curl. So what this says is the magnetic field that del cross is saying it curls. And then the J is telling you the axis around which the magnetic field curls. And it curls around the current. So all of these are equivalent ways of seeing this picture. If you have a current, the magnetic field is going to curl around it in a plane perpendicular to that current. So first we observed that this is what the magnetic field looked like, and then we came up with a bunch of different mathematical ways to write this down. But this was really kind of the first observation that we made about what the magnetic field looked like. Okay, so I promise I will be succinct today. So this is where I wanted to start. I just wanted to remind you of this. And the reason that I wanted to remind you of this is because Faraday's law is almost exactly the same. There is a little bit of a difference though. So let me first draw the picture that's analogous. So what I need is I need a color for, I need someone to select a color for the magnetic field. Put it in the chat. Purple. Oh, Bree got in first. So I like red. But we're gonna go with purple. Okay, can you guys see the screen? Okay, it says that I'm screen sharing, so I'm gonna trust it. All right, so I'm gonna just draw my magnetic field here in purple. Okay, so let me draw the magnetic field. Sorry, I said I was going to do something as analogous as possible. So let me stick with that plan. So now instead of the current, I'm going to draw an arrow that represents a kind of unusual quantity. And most of this unit will be getting used to calculating this slightly unusual quantity. So this unusual quantity is negative dB vector dt. So what Faraday's law says is that there is an electric field that curls around negative dB dt. And so electric field is orange because that's consistent with what the book uses. So we're going to draw the electric field here. And so Faraday is the person who noticed this. So most of what we're doing in this unit, this final unit, is figuring out what our magnetic field looks like, figuring out what our magnetic field looks like over multiple times so that we can calculate a change in the magnetic field so that we can draw this vector and figure out what our electric field looks like. That's kind of the name of the game, this entire unit. I'm going to write down two equations. One of them is the equation that's Maxwell's equation that's analogous to this. So the analogous Maxwell equation is, and again, if this is something that's completely unfamiliar and you don't feel like is helpful, you can totally ignore it. I'm just writing this down because every once in a while, someone's familiar with this notation and they find it really helpful. Okay, so this is the mathematical version of what I said above. This says that the electric field curls around negative dB dt. And then finally, I'm going to write one more version of this that's very useful. And this version is actually related. And the reason that this other version is so useful is because it's related to the voltage. So this is called the integral form of Maxwell's equation. And this says that the voltage, which is E dot dl, is equal to the change in a quantity that's called the magnetic flux. This is not the point of today's lecture. We're going to start working with this after we get really good at making this picture in specific physical situations. So first, we're going to get really good at figuring out what our negative dB dt looks like, and what our electric field looks like. And then after we have a lot of practice with that, so that's what we're going to practice all next week. After we have a lot of practice with that, then we're going to start working with this equation. So don't worry about this equation too much. The reason that I'm mentioning this equation is in case you've seen it before, and also just to point out that this equation is handy because it has this quantity right here that is the voltage. And anytime we have an equation that involves a voltage, it tends to be useful because the voltage itself is such a useful quantity. Okay, so, but let's ignore that equation for now. The really important thing is that what we always want to do when we're working with Faraday's law is figure out what the electric field looks like. And to do that, we have to draw a system over time so that we can figure out the change in the magnetic field. That allows us to use this right-hand rule to figure out what the electric field looks like. So let me show you what that looks like for the exam 4 extra credit problem. Okay, let me pause and ask if there are any questions at this point. Okay. All right, so let's take a look at this exam 4 extra credit. So uh, all right, I think there's an extra column in here. There's a lot in this one. We're actually going to ignore the first couple ones. We'll start talking about those a little bit more next class. Here's what we're going to focus on here. So we are going to take a look at our system. We're going to draw it at 2 different times. The reason that we need to draw any system at 2 different times in this unit is because of this DDT. So anytime we're talking about the change in a quantity, we have to have some kind of final and some kind of initial. So as soon as we introduce that derivative into our equation, we know that we're going to have sort of a final situation, an initial situation, and we're going to be taking the difference between the 2 of them. So we have to start we're now going to have to draw the system multiple times. And then we're going to have to draw the magnetic field at both of those times so that we can calculate the change. At that point, we're going to be able to use the right-hand rule to figure out what our electric field looks like. So the goal of this particular worksheet is to help you walk through that process. So here I have a system drawn. I want you to take a look at the system and ask me questions about what's happening with this system, because it's not immediately obvious what's going on here. So I'm going to give you guys a minute to look at this and try to figure out what's going on, and then ask me and make sure you're understanding it correctly. And then this is a very simplified sketch of the system. So we'll make sure that you understand what part of the system this is. It's going to ask you to draw the magnetic field at 2 different times. Okay. All right, so my question is, do you guys want to be in breakout groups so that you can talk while you're doing this? Or does everyone want just 3 minutes of quiet time to read about the system?
I think 3 minutes of quiet time is good.
Okay, all right, I'm going to go ahead and mute myself. I'll check in 3 minutes. Okay, does anyone want another few minutes to read about this?
I think we're good.
Okay, all right. Is anyone willing to walk me through how they're understanding this system?
I think I could try to give it a try, Dr. Roberts.
That would be awesome. Yeah,
Uh,
okay, go ahead. What's happening here?
so maybe I'm looking at this the wrong way, but I guess I'm considering the question, and it says draw the magnetic field through the upper loop at the time t as it goes to time 1, and that the field is getting stronger. And so in this moment, my understanding is that the magnitude of the arrows that are surrounding the coil there are just getting bigger so that they curl in quicker and thus stronger.
Yeah, okay. So one question is I think that I agree with most of what you said. One question is which coil, because there's actually two coils in this picture.
So I'm thinking it's the primary, the copper looking center, not necessarily what's on the outside, because the field lines are being generated through the copper looking piece, it looks like.
Yeah, so there are actually two copper looking pieces. There's this one and this one.
Oh, okay.
Do you see that?
Yeah, now
So
I see it.
yeah, and this is a setup that's typical for Faraday's law. So what's this is trying to indicate is that there's this primary, what I would call a primary copper coil. It's hooked up to a power supply. See this little like squiggle that it's hooked up to?
Okay.
This is the symbol for an AC power supply. So this is actually hooked up to like the wall and then to the power company. And there's current that's being driven through this lower coil. Um, Okay, I'm not sure. Does that sounds like your picture or not? I'm not sure.
Yeah, that sounds about right.
Okay.
I didn't actually even see that upper coil because it's kind of light. Um, I think I'd probably still have the same evaluation of it. I would just say that the arrows are longer because the field is stronger. I forget which of my explanation you did not agree with just yet.
Yeah, so I think I just wanted to make sure that we were thinking about the same location. And
Okay,
so when I think that I agree with you that like the magnetic field is increasing. I don't think it's actually going to curl any, like I don't think it's going to have a tighter radius, but I
okay,
think that each, like you said, each of these vectors is going to get large, like longer. Or I guess if we look at this picture is kind of showing unit vectors, would get color, something
okay,
like that. But I think we agree about what's happening with that. And what this bar is representing is this upper coil. So we
okay,
have this lower coil and current, it's at that one is actually hooked up to a power supply and current is running through it. And then in this upper coil, it's not actually hooked up to anything. It's just sitting there in inert little coil. If any of you have a like an RTD card or an ID card, there's a coil in those. It's not hooked up to any power supply, but it's used to badge in on those RFID scanners. So this is a coil like that. It's not actually connected to anything. So that upper coil is what's down here. Okay. Okay, so I think maybe we agree on what's happening. But now we agree also on where we're looking. So we're looking at this upper coil and the magnetic field is increasing in magnitude from time 0 to time 1. Okay. Okay, great. Does anyone have any questions on what's happening with this system? Okay. Is anyone willing to explain how they would draw this, how they would draw the magnetic field at t equals 0 seconds, and how they would draw the magnetic field at t equals 1 second.
Would this be something that would almost be like a graph, like you're plotting time versus power, so it would have some movement, or is there some other way that we would show this, I suppose?
So I guess here I'm kind of asking you to make a drawing that's almost exactly like this drawing. So this is meant to be a drawing that shows you what the system looks like at t equals 0 seconds.
So I guess I would draw that upper bar there, and then in this moment, I would copy the exact length of the arrows that are going through it currently. And then at 1 second, when the arrows get longer, when the field is stronger, I would do the same thing for the other side, just longer arrows.
Okay, so kind of like this for 0 seconds.
Yeah, that looks good.
Okay. Okay, great. And then twice as strong, so twice as long. Like this?
Yep, looks good to me.
Awesome. Okay, so again, I'm looking at this part of this picture and I'm copying this exact thing for time 0. And then just like you're saying, I'm making them twice as long for t equals 1 second.
Yes.
Yeah, okay, so Bree, you're saying this is a really good point. You're feeling like the arrows would get longer and more curved. Do you feel like this matches your picture, or would you draw something slightly different? Okay, excellent. Okay, so now what we can do is, because we have 2 times, we can actually calculate the delta B. So and the delta B is important because what I need is to have this picture right here, right? I need to know what is the direction of negative dB dt. So to get negative dB dt, I'm first going to calculate delta B. All right, so delta B, the change in any quantity, is always the final quantity minus the initial quantity. So I can draw this in vector ease. And I can say that I have like an arrow that's longish minus a shorter arrow. And I would say that that is an arrow pointing upward. If you're not comfortable graphically doing these kind of vector operations, you can plug in some fake values, right? So this is why I have this. I'm going to erase this and then redraw it just so that it's like easier to follow by eye, right? But you can draw in a coordinate system, and then you can write down what your vector looks like approximately in coordinates. So this to me looks like it's in the positive y direction. So I'm going to call it 0, 2 Tesla 0 minus 0, 1 Tesla 0. And that is going to be equal to 0, 1 Tesla 0. So the values themselves aren't important. What's important is that their relative size and direction is correct, right? So the point here is that this one is still in the positive y direction, but it has a larger magnitude. And this one is also in the positive y direction, but it has a smaller magnitude. And that ends up giving me the right direction information. So both of these methods kind of tell me that my delta B is upwards. Any questions about this? So I'm almost to the point. Okay, so the whole point of this is drawing this at 2 times so that I can figure out a delta B. I'm just going to point out what part in the rubric that is. it's here, I'm drawing the system at 2 different times. I haven't made it super clear what's changing. What's changing here is the current running through this lower coil. So I'm hooking it up to some kind of supply that's variable, and I'm increasing the current that's running through the coil, and that's what's making the magnetic field stronger. So if this were an exam problem that I were doing, I would want to make that clear. I've now drawn the direction of the change in the magnetic field. Here's my delta B. And now I am ready to figure out what the electric field looks like. That is what this question is asking you for. Draw the electric field. And so we've done all of this in preparation for figuring out how to draw the electric field. So let me walk you through my thought process for this. So I go back over to my lecture plan. So the electric field is going to curl around negative the change in B. So over here, I've drawn the change in B. Negative the change in B is pointing in the opposite direction. So I can also see that, right, again, I can kind of like, I can know that when I multiply a vector by -1, it's going to be opposite the original vector. I can also like write this out in vector form. If I multiply 0, 1 Tesla 0 by -1, I'm going to get 0, -1 Tesla 0, which is pointing downwards. So whatever you have to do to convince yourself of your direction of your vectors, go ahead and do it. And I'm a really big fan of writing out sample values because that's kind of I would say, it's very reliable. It's easy to get turned around, and this is one way to double check yourself, or make it less likely that you get turned around. So pointing downwards. So now this is a bird's eye view from the top. I'm not sure that I actually say that, so let's write this in. This is meant to be a bird's eye view from the top. So let me draw that over here. It's like our eyeball. Is that an eyeball? Those are supposed to be eyelashes. I don't think that's helping. Okay, we're looking down. Let me try drawing that differently. Let's imagine that we have a little person and they're like laying down and they're looking at it. They're just done sitting up, so they're looking straight down on this thing. So that's the perspective here. So what I'd like you all to think about is, here we drew the negative change in the magnetic field in this perspective. If we change to this perspective, how can we draw? Where is the negative change in the magnetic field going? So I'm just gonna pause for a minute, let you think about that, and then we'll check in and see if we all agree. And this matters because once we know the direction, the negative change in the direction of the negative change in the magnetic field, then we can use this right-hand rule that we have to figure out what the electric field looks like. So that's why we're figuring out what that vector looks like in this perspective. Okay, is anyone willing to share what direction is the negative, the change in the magnetic field pointing in this perspective? Up, down, left, right, into the page, out of the page? None of those. Is anyone willing to take a guess? Dylan, into the page. Okay, so Dylan is saying that the the negative change in the magnetic field is going into the page. All right, like this. Does anyone agree or disagree with Dylan?
I think I agree.
I also agree.
We have a lot of agreement. I also agree. I'm not great at perspective drawings, but I'm not terrible at them. So yeah, we have enough agreement that I feel like I'm pretty confident about this. So now what we can do is we can come over here and we can match with this picture. So the idea here is that we take our thumb and we're going to point it in the direction of negative the change in B. And then our other fingers are going to curl around and show us what E looks like. I don't have video on. Does anyone? It's kind of tough with video as well. But so if you all kind of mime with me, if you take your right hand and you point your thumb into the page, are your fingers curling clockwise or counterclockwise?
Clockwise?
Clockwise. That's right. So the electric field is going to be curling clockwise around this top wire. So this is really interesting. So this is the wire that's not connected to anything. So so if we look at this picture, right, this lower coil is connected to a power source and we're driving current through it. And this upper coil, just by virtue of being near this coil that's connected to a changing current supply, has an electric field that's wrapping around its wires. And this electric field is going to be able to drive current. So just by being near something that has a current that's changing, we can have an electric field that we can harness. And that's how all these RFID scanners and cards work. And that's it. That's what you need to do for tonight's reading assignment. Any questions?
I'm so sorry. What do we have to do for tonight's reading assignment? I have.
Oh, so the idea here is what you need to do is this this exam for extra credit. You can find a clean version on Canvas in the exam for extra credit assignment.
Okay, thank you.
Yeah, absolutely, Zena. I'll update that so that it's due like tomorrow morning. Does that work okay for you? Yeah, submit it to the reading assignment. That's right. There's more of the exam for extra credit that you'll need to submit, and we'll work on that as well in class. But we just kind of want to get this one started because this is, like I said, this is what we're going to be doing for the next week, and probably the next week plus a little bit more, is just looking at systems that are changing in some way, drawing them multiple times, drawing the magnetic fields along with them, and figuring out what our change in B looks like so that we can figure out what the electric field looks like. We're just going to practice this over and over again with all kinds of different systems. Yeah, and then that will really help us when we go to actually calculate the voltages, because we'll know what the magnetic fields look like, what the electric fields look like, and that will make the mathematics much easier. But I don't own, excuse me. I don't know about much easier, but it's definitely difficult to do the mathematics if you're not sure what direction those vectors are in. Okay, I'm going to suggest we call it a night if there aren't any questions. I'll update the due date on the reading assignment, and I will see you guys on Monday and we can continue practicing this. Thank you guys so much. I know this week has been hectic, so we'll hopefully be back to normal next Monday.
Thank you.
Thanks, everyone.